Okay, more problems from 4.6, number 19. This is the sliding ladder. A 13-foot ladder is leaning against a house. When its base starts to slide away, by the time the base is 12 feet from the house, the base is moving at the rate of 5 feet per second. A, how fast is the top of the ladder sliding down the wall at that moment? Well, this is going to be, Y is going to be vertical, and X will be the horizontal position. So the ladder is moving this way, so when X is 12, so that's when my horizontal position, when the base of the ladder is 12 feet away from the house, that's going to be X, so X will be 12, and it's moving away at a rate of 5 feet per second, so that's going to be dx dt. Dx dt will be 5 feet per second, and they want you to find out how fast it's sliding down the wall, so that's going to be find dy dt. So again, we have the Pythagorean relationship. That's going to be our geometric device we use to link this together, and we know that X changes and Y changes, but the 13 does not. So I've got X squared plus Y squared equals 13. I can take the derivative of this implicitly with respect to time. So 2x dx dt plus 2y dy dt equals 0. I'll subtract 2x dx dt from both sides, and I end up with 2y dy dt equals negative 2x dx dt. And I'm looking for dy dt. So I'll divide both sides by 2y. So I got negative 2x divided by 2y, or negative x over y. Okay? Now I know the x is 12. That's given. And I know dx dt is 5 feet per second. That's given. How am I going to find the y? Well, I know at that moment the x is 12. That's when x is 12. The y is, the ladder is always 13. That's the y is always 13. That's the ladder. So what will the y be at that moment? So we're just going to take a little picture of that moment. Well, if we think about that moment, we have a 5, 12, 13 triangle. Now you can work it out if you want. This is a familiar right triangle, but if you have any trouble with that, you know that you could just say that, I guess you could say over here, you could call this y. 13 squared, so y squared plus 144 equals 169. So y squared equals 25. All right, so you can work it out like that. Okay, y squared plus 12 squared equals 13, so just use the Pythagorean theorem. So y equals 5. Okay, so I can just put this in. So negative x over y is negative 12 over 5 times 5. 5 over 5 is 1. So dy dt is just negative 12 feet per second. So that's the negative means it's going down. Okay, that's why it's negative. The top is sliding down, so it's negative. Okay? And the bottom is moving in the positive direction, so that's why this dx dt is positive. Okay? Okay, letter B. At what rate is the area of the triangle formed by the ladder, wall, and ground changing at that moment? Well, what's the area of the triangle? Well, the area of a triangle is 1/2 base times height. If I look at my triangle, my base is going to be x, and my height will be y. So 1/2 x times y. We want to find out how fast is the area, at what rate is the area of the triangle formed, changing at that particular time. So I can just take the derivative because I want to find out what dA dt is. So that's 1/2, and then I'll just take the derivative of x times y, and I'm going to have to use the product rule. So first times the derivative of the second with respect to time. So dA dt equals 1/2, and then x times first times the derivative of the second, dy dt plus the second y times the derivative of the first dx dt equals, and then 1/2, and then I'll just substitute my values. X was 12. dy dt was negative 12. Okay. Y was 5. And dx dt was positive 5. So all that is data from above. Okay. And then if I multiply, I get negative 144 plus 25. So 1/2 negative 144 plus 25, which is 1/2 negative 119, if I add these up. And if I divide that by, or negative 119 by 2, I get negative 59.5, and that would be feet per second. I'm sorry, feet squared per second, because that's area. Okay? So the area is getting smaller at the rate of negative 59.5 feet per second. All right? So as the ladder is sliding down like this, you can see the area is getting smaller and smaller and smaller. Okay? That makes sense. So I have a better ladder. I don't have a better ladder here. But I think you get the idea. Okay? As the ladder slides down, you can see that the area is getting smaller and smaller and smaller. Okay? And we have a C part. At what rate is the angle between the ladder and the ground changing at that moment? So this is my angle, theta. And I want to get some kind of relationship involving theta so I can take the derivative. So I could use several different forms, but the easiest one to take the derivative, I guess, would be just as easy, would be tangent. So I can say the tangent of theta equals y over x, opposite over adjacent. Okay, y over x. Because these are my variables, so that's going to be the best to work with, my variables. So if I take the derivative of both sides implicitly, I get the derivative of the tangent is a secant squared d theta dt, and I'm going to have to use the quotient rule here. Okay, that makes it a little bit different approach. If this was just x, or even just y, then I could do it using the inverse tangent. But because this is a quotient here, it's going to be it would be a lot more complicated to do the inverse tangent. Because of my chain rule, so it's a little bit better in this case to take the secant. And I'll show you how to handle that secant in just a moment. Because the issue is we're still going to have a theta, but we can work this out anyway, so you'll see. So if I take the derivative of the tangent, I get the secant squared theta d theta dt, because we're taking the derivative with respect to t, and then I'm going to have to use the quotient rule. Low d high dy dt, less high d low dx dt, denominator squared below. Okay, so remember the quotient rule. And then we have to find values for this. Now this is where we have to do a little bit of extra work that we avoid when we're doing the inverse tangent. But like I said, because of this issue, this is a little bit better just to use the secant squared rather than the inverse tangent approach. Okay, so how am I going to find out what the secant of theta is? Well, if I look at my triangle, remember the secant is 1 over the cosine. The cosine is the adjacent over the hypotenuse, so the secant is the reciprocal of that, with the hypotenuse over the adjacent. So the secant at this moment of theta is 13 over 12. So that's the secant, and that's going to be the secant squared, so this is going to be 13 over 12 squared. And that's d theta dt. And then I know that at this moment, x is 12. And dy dt I found earlier as negative 12 minus, and y is 5. And dx dt, which was given at the very beginning of the whole problem, was 5. And all over x squared, which is 12 squared. So we got a little arithmetic, negative 144 and negative 25 over 144. 12 squared is 144. This is negative 169 over 144, and this happened to be 169 over 144. So if I divide both sides by this, 169 over 144, I get negative 1. And it's in radians. That's our angle measure. Okay, so it's in radians per second. So it's negative 1 radian per second. And unless otherwise notated, whenever you're finding angle measurement, it will be in radians per some unit. Okay, I hope that helps.